Hello. This is going to be a little lecture about the COVID-19 outbreak. I'm going to introduce you to a little bit of the mathematical modeling that goes on to understand the mechanisms of the outbreak and how our interventions can mitigate some of the outcomes. Like a lot of sciences, we are able to describe rates very easily, or at least most obviously, whereas total changes are tougher to understand. And so what that means is when we start to model things, the processes of infection in epidemiology, it ends up primarily being encoded in differential equations. I'm going to show you the model that people have been generally using for the COVID-19 outbreak. Okay, it's called the SEIR model. Now, the idea is we have some population here, and in this exercise I'm going to refer to Nova Scotia. And if we drag a person out of that population, that person can have one of four categories. They can be S, and that refers to susceptible. And susceptible individuals are individuals that have not yet gotten the infection. They're let's say, healthy. They could also be in the E class, and the E class refers to exposed, sometimes called the latent class. And the idea here is that an individual who is in the E class has been in contact with someone that is infective and has gotten the infection, but they aren't yet infective to others yet. So the infection hasn't manifested itself sufficiently enough that they would be infective to others. It's taking a while to incubate in the body. After some period of time in the exposed class, that individual would move into the I class, which is infected. So these people fully would be infected with, in this case, COVID-19, and that infection would last for some period of time. And the statistics on the average length of infection time is known. Should the individual recover from the infection, they would move into the R class, which is recovered. And so in that way, the entire population of Nova Scotia lands in one of these four categories. Everyone in Nova Scotia right now is either S, E, I, or R. And of course, the vast majority of Nova Scotians are susceptible right now. They haven't been in contact with anybody. There's, I don't know, about 100 infections or so, maybe a few more. All right, so we want to model how these various subpopulations evolve over time. And so we're going to build up a set of differential equations to describe their evolution. We'll do it in the order that they appear, S-E-I-R. So how does the S category of the population change? They change according to the derivative, the rate of change of S. And the way in which susceptible people change is through one mechanism. You can become exposed to the infection and thus move out of the susceptible category. There's no inflow into the susceptible population. And so if you think of the compartmental analysis approach, we have rates in and rates out. There's no rate in to the susceptible population, but there is a rate out. And the rate out is caused by susceptible people coming in contact with infected individuals. And so I'm going to write a term here that's going to characterize that particular interaction. Okay, so there's a minus beta S times I over N. All right, and I want to take this term and I want to really kind of break it down. So let's pull it over here. Minus beta S I over N. So what's going on here is infections occur due to interactions between infected people and susceptible people. So it's the infected person that coughs on a susceptible individual, or they have COVID-19 virus on their hand and they shake a hand of someone else who later touches their face. These kinds of interactions that happen between S and I individuals. You need an S and an I in this interaction to come together in some way in order to have this transmission of the infection. Now, we have this divided by n. That's just scaling by the size of the population, this interaction. What this is referring to is the law of mass action. And it's a generalization of how different components can interact to create a certain rate of flow in this case, in the S category. So it's a flow out of S. And it's also used to model chemical reactions where the S and the I will be the concentration of the reactants in the chemical reaction, for instance. So if you have a lot of S and a lot of I, then you have a fast rate. And if you have a very small amount of S or a very small amount of I, you have a very slow rate. That makes sense. Very few infected individuals or very few susceptible individuals, and you will not have a high rate of transmission. Either there's no one to infect anyone else, or there's no one left to be infected in those two cases. Okay, I want to drill down a little bit into this meaning of beta. So let's take this term. I'm going to write it as minus beta times I, and I'm just going to put S over N here. So imagine initially we're just at the start of the outbreak. The susceptible population is basically everybody. Now N is the total population. So this S over N term right here is pretty much 1. And so what this is saying is the rate of change of susceptibles out of that class into the exposed class when they get the infection is governed by minus beta I. So beta has its own interpretation here. Okay, so this beta is in a unit time, and let's use days as our time unit here. So it will be the average number of infections per day that's caused by an infected individual. Okay, so average infections per day caused by an infected individual. And so if beta was equal to, let's say, 0.25, that would mean about every 4 days, the infected individual would infect some other individual. This is connected to the basic reproductive number R0 or R0, but it's not quite the same thing. R0 would be the same thing over the length of infection, not per day. The average infections caused over the length of the infection by an infected individual in a completely susceptible population. Okay, so we know how the S category, the susceptible category, loses individuals. They don't gain individuals because you can't become resusceptible in this model. If you are susceptible and you become infected via this rate that I've described, this law of mass action, then you move into the exposed class. And so the next equation is di dt. It's the rate of change of the exposed class. And this is basically gathering up those individuals that just left the S class. So the flow out, the rate out of S is the rate in to E, much like the salt in the bathtub kind of problems. So we have beta Si over N in the exposed class. All right, now the rate out of the exposed class is caused by people no longer being characterized as exposed, but being characterized as fully infected. And this is governed by, again, some rate, some proportion of the E class will be leaving, and we'll use a sigma to indicate that. All right. Now, again, let's take a look at this. Sigma is equal to 1 over the average length of, let's call it incubation. It's not quite the right word, but let's call it that. This is basically how long the infection will be in your body on average before you're fully infective to others. And most of the recent models that have come out on this have estimated this to be about 5 days. So our sigma is going to be about 1 over 5 in this model. And so that will create this outflow of the exposed class, and that will flow into the infected class. So now we have the rate of change of the infected class being the sigma E. It's those that have moved out of the exposed class and are flowing into the infected class. So that's the rate in there. What is the rate out of di dt? Well, you can leave the infected class through two routes. The majority will recover, and I'm going to use a gamma to refer to that rate. So there's some rate of recovery that is dependent on the length of time you spend in the infected class, or you can die. That's another way to leave the infected class, and I'm going to write it as minus mu, get that out of the way, minus mu I. So we're going to look at these two components, make sure we understand them. I'll drag you over here. Okay, minus gamma I, that's a flow out, it's a negative value, that's the rate of change of I being negative, so it's losing individuals due to recovery. And this gamma is the recovery rate, which is approximately 1 over the average length of infection. And most of the models right now are converging around an average length of infection. This varies from person to person, by the way, but we can average this out, and it's about 11.1 days. So this rate would be 1 over about 11.1. Okay, so they're lost according to recovery, or they're lost according to death. Okay, this is the death rate. We're going to drill down into that a little bit more deeply in this model, so I'm going to leave that in terms of a discussion, but that's what's going on. It's a loss due to death. Now, if you're lost due to a death, you don't appear in any other category here. We could have set a fifth differential equation that gathers up the dead individuals and stores them there, but there's not really any point to doing that. We can keep track of the dead in this model through another conduit. So the final thing is the recovered class. So the rate of change of the recovered class is simply the flow in of the recovering infected individuals. All right, and so this is the gamma I term. So really this SEIR model framework is really just characterizing taps in and out of these four categories, and the tap out for one is typically the tap in to the next. So we have these connections here where the susceptibles become exposed, and then the exposed become infected, and they connect by these two terms, and then the infected become recovered, and so they're connected by these two terms, and then there's a secondary loss of infected individuals through death. Very, very simple modeling framework, lots of parameters, but most of the parameters we know. The beta is the real mystery parameter. The beta is it characterizes the transmissibility. Remember before we said it's the average infections per day caused by an infected individual. So the beta is characterizing how infective is this. And that depends on a lot of things. It depends on the mode of transmission through these little droplets from people. It depends on how well the virus is at setting up in a new host. It depends on primarily human actions. So social distancing is going to greatly influence the beta. How frequently we wash our hands, our public health outreach in order to change people's behaviors. All these kinds of things are going to influence beta. So beta is somehow characterizing, it's the one thing in this model that we can control, and it's characterizing both the inherent properties of the virus and also our human response to the infection. It's all mixed up into one single number, beta. All right, so I'm going to come back here. What do we typically do with this? Generally speaking, with these kinds of models, we are not into analytically solving them. That is, we're not looking for a mathematical equation that describes S, E, I, and R. It's far easier just to numerically simulate them, especially if we have a good guess for most of the parameters. Then we can do some parameter exploration for maybe the things that we don't know and make some predictions based on that. So what do we do with this? We solve them numerically. And all we need is a very basic differential equation numerical solver. In calculus, we learned Euler's method, and that's the one that I'm going to use and is very typical to use. When I solve this, I get an S of t, an E of t, an I of t, and an R of t, curves that describe the evolution through whatever time window I'm curious about, describes the evolution of these four populations. Particularly, we're interested in the this curve here, the I of t. How does the infection evolve through time, and what does that curve look like? This is what we are trying to flatten in terms of our behaviors, the famous flatten the curve language we've been using a lot. Now, I've described the SEIR framework. The beautiful thing about this approach, this mathematical epidemiology approach to compartmental analysis, is you can implement a bunch of different strategies in this, and you can modify the different groupings, the SEIR groupings, to be entirely different depending on what kind of outbreak you might have. So maybe with HIV or Ebola or tuberculosis, you might have different categories. You can also have a vaccinated category. You can have carrier categories for different outbreaks. Whatever the specifics biologically are for a given outbreak, these equations can be modified to manifest that. So it's very flexible that way. Now, one thing that people have been noticing with COVID-19, there's a highly age-dependent mortality rate. The very young are basically not dying from COVID-19, right up until middle age, basically, the very, very low mortality rate, until you get into the 60, 70, 80 plus categories where the death rate starts to skyrocket. And that's, of course, we all know this now. This is repeated ad nauseum on every media outlet you can get your hands on. I'm going to show you some data on this. And the data I'm going to show you is from some of the earliest outbreak data from Wuhan in China. So this is the fatality rate by age that they've observed. They're, of course, ahead of us by, maybe a month and a half or so. So the data is coming out there, and we can parameterize our models based on the outbreak that's already taken place in Wuhan. And so we can see here very, very low mortality rates, far less than 1%, 0.2% from 10 to 19, actually 0% from 0 to 9 years of age, although I think there's been one reported death now in China from someone under the age of 10, possibly a few others around the world now. Extremely low mortality rate, though, right up through until you start hitting middle age into the 40s and 50s, and then it just starts to ever so slightly climb to a mortality rate around 1%. And then it climbs up rather precipitously up to a rate of almost 15% mortality, which is extremely high if you're over 80. Now, this kind of data is inherently problematic because it relies on complete knowledge of infections in the population. And generally speaking, this is never known. We know only what we test, and we certainly don't test everybody. And the vast majority, probably 80% of cases, are very, very mild for COVID-19. And so often we don't know the full extent of the infection because many people are becoming infected and are not noticing really or are not being tested. And so they don't land in the statistics. So these rates could be potentially less than they are, but we can only use the rates that we have to the best of our ability here. And as time goes on and the data becomes better, we'll get better estimates of these things. I saw one set of data that came out, and it had the death rates maybe about half of what appears here. It was about 7 or 8% for the 80 plus category. Nevertheless, we'll use these because this is published data. So then the question arises, if I have this age-dependent data, how do I incorporate that into the SEIR HIR framework. And the way around it is this. I'm not actually going to use differential equations anymore. Instead of having a population where I just basically keep track of the counts of the S, E, I, and R subpopulations, I'm going to instead model a population of individuals. So every individual gets modeled in this population, and every individual at any given time, they carry an age, and they carry a state, and that state is the S, E, I, or R state. So it's an individual-based model, not a differential equation model, although the structure of it, the flows from category to category, follow the same rules. In this case, then, if you become infected, you land in the exposed class for 5 days, and then you transition to the infected class for about 11 days, and then you transition either into death or into the recovered class. However, the transition out of the infected class via dying depends on the age. So every individual has a different rate attached to them according to which of the age classes they land in the above data. So obviously if you're assigned an old age, like 85, you have a high chance of dying versus if you were assigned a low age. And then the idea is you take your population and you stratify the age in that population according to available demographic data. So I just went to StatsCan, and you can get the Nova Scotia age demographics. And so we take the population of Nova Scotia, which from StatsCan can be best estimated as about 971,395 individuals, just a hair short of a million. And then we break that population into the various age categories. We have a slightly older population in Nova Scotia than maybe some other jurisdictions, but this 971,000 people, for instance, in the 0 to 9 age category, it's about 9.6% of the population. The 10 to 19 category, it's about 11.6, and so on, right up until you get to the 70 to 80-year-old class, which is about 6.9%, and then the 80-plus class, which is 4.3%. So relatively smaller proportions of the population, however, a much higher death rate from COVID-19. So we have all this data, we impart this data into the model, we individualize the SEIR model, and we code it all up into MATLAB, which I've done. And so we're going to look at some results now. The results are all couched in terms of beta. And just to remind you, beta is the average number of infections per day caused by an infected individual. So if beta is equal to 0.1, it takes about 10 days for an infected individual to infect another individual. If beta is 1, they're infecting on average 1 person per day, which is a very high rate. This is, in actuality, is governed by also S and I over N. You saw that in the differential equation. It's the same thing in the individual model. So as the susceptible individuals become far smaller, this rate is going to be slowed by the lack of available susceptible individuals to infect. So that's all built into the model. Of course, this is a gross oversimplification of how humans actually interact, but mathematical modeling, of course, is always an attempt to retain the essential dynamics in a simplified form so that we still gain insight, but lose some of the inherent complexity that exists. If you want more complexity in terms of how individuals actually interact, there are network-based models that look at these features as well. We won't do that. First off, we're going to look at a value of beta equal 0.5. Now, beta equals 0.5 is quite high. An average infected individual every 2 days or so would infect another individual. So what does the curve look like for infections under this case? Here it is. It's a nice MATLAB graph. The time axis down here you can see is in days. I go to 200 days in my little simulation. 6 months is about 180 days, 182 days. So you can see 200 is a 6.5, almost 7 months. The total infections that we would see in this case of beta equals 0.5 is 967,000. That's basically the whole population of Nova Scotia, save for a few thousand. You can see the infection curve jumps up here, and the units of the blue is in hundreds of thousands of people. So at the peak, about 70 days in, two and a bit months, you get this peak of almost 500,000 people at once being infected. And that's not infections per day, that's not new cases, that's people who are infected at one time. Now, of those 500,000 people that are infected at one time, about 10% have been, around the world, have been hospitalized. So that's 50,000 people at one time who need hospitalization, which would far surpass our capability to house people in hospitals and provide them with ventilators and care and all the things we need to do in the hospital. The black curve here shows you the number of deaths, and this is all containing all that age-dependent information. And you can see it comes up here. It's just a hair above 19,000 people, just a hair under 20,000 people would be expected to die in this scenario. 19,000 people in Nova Scotia. That's a lot of people. And we don't want a beta equals 0.5. Okay, for two reasons. The overwhelming of our healthcare system means that the fatality rate is higher. And if you look at places like Italy, the fatality rate is significantly higher than places that have been able to control the size of the outbreak. Currently in the US, things are getting completely out of control, especially in New York. You might be hearing stories coming out of there. They are getting overwhelmed in their health delivery systems due to the number of infections. We don't want this very sharp peak as such. And the sharp peak happens when the beta is very large. That means the disease is transmitting through the population very quickly. We lower beta by, well, we can't do much about how the virus behaves, how it moves via droplets and infects other people and so on. But we can change how people interact with other people, and we can effectively lower beta that way. So the next graph I'm going to show you is a smaller version of beta. Let's say we've gone through some social distancing measures and so on. To this last one, this bump occurred, give or take around 75 days in was the peak. And we've been able to reduce beta by 0.3. Well, what's the difference now? Beta equals 0.3, still a lot of total infections, still almost everybody. Now we're missing, 42,000 people or so, 41,000 people. The number of dead, still very high. It's a little bit lower than it was before, but still up in the 18,000, 19,000 category for number of people. We have, however, reduced this bump here. This bump only goes up to about 350,000, whereas before it was up to around 500,000. Now that would translate into roughly, let's say, 35,000 hospitalizations. So we've reduced it by about 15,000 people at once requiring hospital services. That's significant. However, still probably at the level where it would overwhelm our ability to care for all of these people. You can see the bump also, if you compare, now we've pushed that peak out to 100 and maybe even a little bit more. So we are seeing, borne out in the mathematical model, the idea of this flattening of the curve. The flattening of the curve reduces down the value of the peak, and so there's that reduces the total strain on our healthcare system, but it also pushes the bump out further in time. That's slightly problematic. That means we're stuck in our homes more for a longer period of time. All right, so let's say we're not happy with beta equals 0.3. We continue our social distancing measures. Now we go on effective lockdown, these kinds of ideas. We're going to keep pushing beta down. All right, now we're down to beta equals 0.2. Okay. Well, what happens? Total infections are down. Now we're down in the 800,000 range, right here. The total number of dead is now, maybe 16,000, right around here. Okay, so we've reduced that number. We've significantly dropped the peak down to about 200,000 people, so that might be 20,000 hospitalizations, so less than half of the worst case scenario that I started off with. What else has happened? Look at this bump, how far out in time it's traveled. 5 months down the road, basically, 150 days. as opposed to 75 days. So it's now twice as long to see that peak manifest. And just by 200 days, which is 6 months and a bit, we still haven't seen the infection move through the population. 6 months. We're only a month in here, folks. Okay. Flattening of the curve. We have gone from this to this, and now down to this one. So this progression of reducing beta is reducing the strain on our hospitals, slightly lowering the total death count, not significantly, but slightly, but pushing out in terms of time how long we have to maintain these measures for. And so that obviously has costs for probably let's say our mental health. I'm home with my kids, and that there's some mental health costs there, but also a pretty steep economic cost as well. Okay, a lot of people are not working. All right, now let's get into the regime where beta is getting quite small, maybe crossing some critical threshold value. So next, beta equals 0.15. Now, the average length of infection is 11 days in the model. So the beta is the average number of infections per day. And so if you infect 0.15 people per day, then that's about, let's say, 6.7 days. In 6.7 days, you would infect one other individual. So you're still infecting more rapidly than you are recovering. It takes you 11 days to recover, but about 6.7 days to infect someone. So there's still going to be growth here, but we're getting closer to that trade-off value. Okay. In this case, basically, I don't have a long enough time axis to watch the outbreak happen, but the outbreak is still happening. Okay, you can see it start to climb here, but it takes beyond 200 days to occur. And you can rerun this, for 800 days, and you can see the bump happen. The bump still happens. This is what I would characterize as probably a worst case scenario, because we will still see, if you let this model run long enough, the infection spread through the population. It just takes a hell of a long time. We're into like a year or so to see this thing borne out, maybe 2 years. So this is the threshold of flattening the curve, where we've really, really flattened it. It's super slow, this bump. It might, peak out at a relatively small number of total infections. But the period of time that we have to spend in isolation is 200 days, and probably 400 days, 600 days, 800 days. We really don't want this scenario. I'm going to now push beta beyond this value. Let's say we're getting even better at our social distancing protocols. Okay, we want to look at some the bright side of this. So let's say I had 0.15. We can get beta down to 0.05. Now I want to talk about a threshold that we've just passed through. If I am taking 11.1 days or so to recover, I'm going to look at the rate 1 over 11.1. That's the rate out of the infected class. The beta is the rate at which I infect other people. Now, before I had, in the last graph, okay, so 0.15 is up here. 1 divided by 11.1 is, this number is about 0.09. And now I've just moved across this threshold into 0.05. So at this rate, I am infecting people on average every 20 days, but I'm taking only 11 days to recover. So the rate at which the disease or the infection spreads out into the population is slower than the rate of recovery. And this effective trade-off is what governs this reproductive number R 0. So what happens when I pass through this value? Well, watch. The number of initial infections, which, by the way, in this entire simulation process, I let 4 infected individuals enter the population. So that's how I start this off. 4 people are infected. But it doesn't get going. You can see it kind of jumps around The total number of infections was only 7 people, and it dies off after about 20-25 days. So in this case, we have such effective social distancing measures that we are able to contain the outbreak. The population does not get infected. And in this case, 1 person has died, but that's actually quite high for having only 7 infections. It's all based on probabilities here. So there's some stochastic random nature to this, but in this example, 1 person happened to die out of the 7. They were probably old. So it is our collective goal to reduce beta as far as we can. We would love to see the case where we can reduce beta down below about 0.09, and thus we would be moving the basic reproductive number R0 below 1. That's the critical threshold for that number. So there'd be on average fewer than 1 secondary infection for every infected individual. If we can do that, then we can have this be the outbreak curve of COVID-19. Extremely difficult to do, and furthermore, it has to be a global collective effort, because if we do it in Nova Scotia and they don't do it elsewhere, then as soon as all these controls are lifted and an infected individual comes back to Nova Scotia, then it gets going again. So we either need a vaccine, which maybe we're 12 months away from, 12 to 18 months at the best case. We either need a vaccine, or we need everyone to get together to eradicate this. That's also extremely difficult. The third option is to allow the outbreak to move through the population, which we might not have no choice in, and in that case, we would eventually get herd immunity, provided humans show a reliable immunity to the COVID-19 virus after infection. There's some preliminary evidence that that is in fact the case. All right, so the final question, now that I've put all the age-structured elements into this model, the question is, who is dying in Nova Scotia? So I scaled beta way back up to a 0.5. So this is the kind of the worst-case scenario of the outbreak that basically goes through the entire population of Nova Scotians. And we ask, when it's all said and done, when it's moved through, how many died? We said about 19,000. And now I can plot a little histogram of the age dependency of those that have died. So here it is. This is a distribution of COVID-19 deaths as predicted in Nova Scotia. And as we expect, very, very few deaths in the 0 to 9 category, the 10 to 19, the very few deaths, very few until we start moving up into the 50 to 59 category. So those in their 50s, there's just about 1,000 individuals in their 50s in Nova Scotia who would die. There's about 2,700 individuals in their 60s who would die. Now these are higher than the actual death rates would suggest, but this is a larger proportion of the population. And so the relatively small proportions of the population, those in the 70 and 80 plus class, so in their 70s and then they're in their 80s and beyond, even though they make up only, I think it was 6% and 4% of the population of Nova Scotia, they represent the vast majority of deaths here. So in this case, it's about 3,500 and nearly 4,000. Those over the age of 80 would die in Nova Scotia. Again, this is a mathematical model. It's a gross oversimplification of how these diseases or infections spread through a population. And there are many intricacies into how humans actually interact, and some will never interact with anybody. And our measures can isolate individuals preferentially who are older and protect these guys, and try to reduce down these numbers right here by putting a lot of effort into making sure the elderly are isolated. But it's really up to everyone here to help this process of protecting the elderly, because it is the transmission through these individuals that make the outbreak lead to these deaths in the elderly. So even though people are not dying down here, they are the ones that are responsible for spreading COVID-19 through the province. So don't go party right here. Don't have daycares open from these guys. And stay at home as best you can. keep that curve flat. But God, we should hope for each other that we don't make the curve just so flat that we can't kill this off, and we're in this interminable isolation. Hopefully we can push it below that threshold of about beta equals 0.09, and we can eradicate this thing. And maybe worldwide, there will be a lot of effort into doing the same thing, and we can claim this as a success. Thanks for listening.